put it down here. This is the one is actually open loop. So this one is the example of the open loop first. So something like, let me check. Okay, so this is the open loop. Okay, so we have this example just now. So this one is the open loop. Okay, so if you have this equation, okay, you compare with the one we have just derived. So this one, can we? Okay. So just now we have this example, ys equals to gp multiplied with the input plus gd multiplied with the input. So one of the input is with the control valve and the other input is with disturbance. So from here, we have derived the equation previously, just now, just few hours ago. So this one, you compare, it will be ys equals to your gp, and then this one will be your us plus gd, and this will be your disturbance. Okay, so all with the function of s. So your output is level equals to your GP is R over A RS plus 1, and your input is Q1S. So this is the input with control valve. So this one also input. So input without control valve, it means disturbance. So GD, S, and your disturbance we use in this example we have. We just compare, then we will get R over ARS plus 1 and then QS. So if you refer to the diagram just now we have, so this one with control valve, it is actually Q1. This one without the control valve is Q. Your output is H. And your S for this one is Q3. I think I'm using Q3 just now example. Yes, Q3. Equivalent to H. So you have two input, 1, 2. Hence, you will be having two transfer functions. So H over the Q1 SS equals to your GP, which is your R over ARS plus 1. The other one will be H over Q SS R over ARS plus 1, which this one is your GD. So this one with the control valve, this one without the control valve. So you need to split this over the first one, then you will get this. Then split this equation into two parts, this one, then you will get H over the Q. So the first one is H over the Q1. So you have two transfer functions. One we name as the GP, process transfer function. One we name as a GD, disturbance transfer function. So this one is process transfer function. And this is the disturbance transfer function. And if you have this, there is no turning point, means your level. The outcome does not actually change any of your input, both of these. You do not have something like sensor to measure the H, and then based on the value you have measured, there is no corrective action because there is nothing there to actually measure the H so that you can adjust the Q1 here. So we call this as an open loop response. So if it is open loop response, you'll be having this one equivalent to HS equals to the whole equation of this. So if you want to draw this block diagram, you'll be having one block, two block, one for GP, 1 for GD. The input for the GP is Q1. For this example, it is Q1. And for this example, the input for this is Q. Okay, and both plus together, plus contribute to your outcome. So I put the scope over here. My outcome is my H level. Okay, so this one will be the H. So this is the one we have the open loop response. Okay. Okay, so from here, you'll be having this open loop response. So this transfer function is without time delay. Same goes to this without the time delay. But what I want to introduce here is actually open loop response, where you have the starting point straight away go to the end. Same goes to the other starting point go to the end. There is no turning back like the previous example we have. There is nothing from these go back to any of the value. So there is no turning point. Hence, this one is not closed loop response. This is open loop. Okay. Now, the example I include here is with transport delay, which is with the time delay. So now you already understand it will be like this one will be the GD because of this disturbance. So this is disturbance. And this one will be the input. Okay. So then this will be your process transfer function. And the top will be disturbance transfer function. And both of these plus together will give you the output. In this case, your output is Y. Follow this simple equation. So you have your Y equivalent to your GD multiplied with the D plus GP multiplied with the U, just like this. So we will always write the transfer function first, multiplied with their input. So we won't actually write U multiplied GP, but we will write the transfer function block just like this. You'll be having your transfer function block first. Okay, like your R over ARS plus 1 multiplied with the input. Your transfer function multiplied with the input. You won't be putting your input here. You will be putting your transfer function block first, then followed by the input. Okay, so you'll be having GP, and then this one will be the input of the GP. This will be the GD, and then this will be the D, input for the disturbance. Okay, so in this case, if this is the one given to you, you will be having this Y equivalent to this GD multiplied with the D. So you will put a function of S, Laplace transform in S response, and then plus GPS multiplied with the input, which in this example, it is US. So this will be the equation you include for this. So now this is the transport delay, meaning that your GD and also your GP is in the form of KE negative theta S over tau S plus 1. So for example, you have KE negative 7S over tau S plus 1. Then you will double click this and include the value of 7. So now we want to actually draw this, drag and drop all the blocks of this in the Simulink window. Okay, so you'll be having this example like this 7. Okay, so go to drag and drop all the relevant block you need for this example. Okay, so I will need this new land model. Okay, so go to drag and drop. So this one you will need step input. So you just go to your library and search for the source, or you can't remember the step is actually in the source, then you just type it here, step, and search for the for this block. So you will find your step input here. Where is my step input? So you will have my step here, this one. So you just drag and drop, then you will get 1. You right click, hold and release, you will get 2. Okay, copy and paste. Okay, then you type this one here, create annotation, type the disturbance, type the U. The question given here is this slide. Okay, so I will copy this slide and put it here. So you'll be having this. Okay, so now you're having your GP is this one, GP. Okay, where you get your transfer function block. So this one is called transfer FCN. So if you want the name of all the blocks, you just highlight everything and then format, show block names on. Okay, where to find this? You just go to your browser. Then this one, it is in the continuous block library, this one. So you go to search for transfer function, which is this. Or you just type transfer FCN, then you can get this block. So you drag and drop these two and you double click. Okay, like for example, I drag and drop. Just now, where is this one? So like this, I drag and drop. By default, it is 1 over 1s plus 1. So you need to have, you ignore the exponential term first. You focus on the 2 on the top and then 50, 15, 1. So you'll be having, for example, this block diagram, the GP. So you double click, you just type the top one so that, for example, it's 2, right? So here the top is 2, the bottom is 50, 15, and 1. So you'll be having 50, 15, and 1. So you have to space a bit. So you will understand this one is 50 s power to 2, 15s plus a number 1. So, okay. So if you can't see the full numerator and denominator, you just have to make it bigger. Drag and make it bigger so that you can see the transfer function. Because the block is too small, so it will just state here numerator and also the denominator. So if you want to see the transfer function here, you just have to drag to become bigger, the block. Then you can see everything inside. Okay, so try. Okay, so from here, same thing, like this is your GD, right? I think I copied the wrong one. So if I this is example 4. Why I'm using example 4? I want to use example 3. So it says this one. Okay, so this one. And then, so we are having example 3. Ding. Okay. So you have your same thing, 2, and then 50, 15, 1. So the other one, you just drag and drop. Means you copy and paste. So you double click and you change to 0.3. So this one is 0.3, 0.3. And then you'll be having the bottom is only 15 and 1. So you just change this to 15. and 1. So they will understand, if you just put two numbers here, they will understand this one as 15s plus, the last one is number, 15s plus 1. So, okay. So if it is too small, you will just see something like this. So you can make it bigger, just drag and release. So you'll be having these two blocks, one for GP and one for GD. So your GP is together with the U. So your GP is this one. So just type it here. Cannot type. Hang. There, I type. So this is my GP. Okay, and the top is my GD. So GD. Okay, so from here, your GP is 2 over 50s power to 2 plus 15s plus 1. And remember, the one given to you is actually with the time delay or transport delay. Like this one. Okay, make it bigger. So you will see here is negative 5s. So just now you have locate this transport delay from here as well. So you just go to library browser and then go to search for delay. So it is actually in transport delay. I also can, also in continuous. So here is your transport delay. If you can't remember which library, then you just type it here, transport delay. Then you can search for this transport delay. So you drag and drop, you will be able to get this. Then you right click, hold the right click and copy paste. So you'll get 2. Okay, so now you just double click this. So the GD, so you focus on the GD here. The exponential term indicates the transport delay, 5 unit of time. So it can be in minute, it can be in second, it can be in hour. So you have to define the unit of time. Let's say this is 5 minutes, for example. So you just double click this and put the value of 5. Time delay, 5. So the rest by default don't touch. Okay, just include this number here. Just like when I want to search for the transport delay just now. Okay, when you drag and drop this one, when you double click, the rest actually don't touch, it's already by default. You just have to change this time delay to the value of 5. Okay, so this is 5 for the GD time delay, and then for your GP time delay also 5 given in this. So you double click, then this one change to 5. Okay, so when you have transport delay block include in your Simulink model, it means your GP and GD is with the exponential term. So e power to negative theta s, the theta is actually the transport delay. Like this theta is 5, then it is delayed by 5 unit of time. Same goes to your GD and GP transfer functions. Okay, then you need this addition block. If you want the rectangular shape, you just double click and then change to rectangular. You want to bigger, you want to make it bigger, then just drag it. If let's say, it's like very messy, right? So you just highlight everything and then right click, go to format and arrange. So is it better than arrange? I think yes. But I have other things here, that's why. Yes. Is it better? I think yes, it's nicer lah. So I go back because I have other block here. So let me remove. Okay. So now you can check the simulation time. So for this one, the simulation time is 80. Okay, so this one is 80. So you change this simulation time to 80. Okay, so this one stop time, right? So you just change, not this window, the other window. This one, yes. So this one changed to 80. Okay, so you have your disturbance is the step input. Your U also step input. So they must give you the magnitude, okay, the M value. So in this case, follow the question given here. They should tell you the unit, okay? Input U and D. They do not tell you the magnitude of M. So I assume it is 1. So I will put step time 1, 0, and then 1, 0. So the original one for your step, you should be having the source here. So I will just check what is the original value given. Then you can compare. So this one, drag and drop. So when you double click, step time is 1, initial value, then final value. So it is a unit step change, means the change by 1 unit from 0 to 1. Okay, so 1, 0, 1, 0. Same goes to this one. 1, 0, 1, 0. Okay, so this one also the same thing, step input of 1. So, and the simulation time is 80, then you can click the run. Okay, then you double click this one. You'll be having this time delay. There is no response for 5 units of time. So you can see the value of your outcome remains 0 for the first 5 units of time. So from here, this is your ultimate value. Your ultimate value will get you 2 point something. So this is the open loop response where you have the equation given. For example, the equation given in the form of ys equals to gp us plus the gd ds. So I give you one example, which is this one, but this one is without the time delay, okay? But the idea is the same. You will need to derive the mass balance, and then you will get an equation, long one, which is this one. Okay, you just have to identify from the diagram given to you which one with the control valve. Like this one, Q1 will be my input. So my output is H. I will get one transfer function GP, H over QI, Q1. Then the other input will be no control valve. Output will be the same, H. The input is Q. So H over the Q will be my GD transfer function. So you will derive the mass balance and identify the transfer function this Q1 with control valve. So this yellow color one is GP, and this one you check this input is without the control valve. Then this transfer function we call as the disturbance transfer function. You split this equation into 2 parts, H over Q1. Then you have this transfer function GP. Then H over Q, the transfer function is GD. Then this is the transfer function. So this is open loop. Open loop means when you join them together using the block diagram, connect them, you'll be having this. So GD, the input of the GP, the input of the GP, plus this GD, the input of the Q, then your outcome is the H. So you just compare, you just change this equation into the form of blocks. Okay, then the example continue with, what if now the, where's my slide? Okay, so now is you'll be having the transfer function given to you with time delay. Okay, 6:26. Okay, so this one is with time delay. So remember, this is the pattern of negative theta s. So the theta, the value of 5, it means the delay of 5 units of time. Then you can see the outcome that you have. You will see there is no value within the first 5 units of time. There are too many. Too many. Okay, I accidentally close. I think too many. Let me close. Okay, so you'll be having the delay for 5 units of time. There will be no value for the first 5 units of time due to this time delay. Okay, let me close everything. Too many things already. I couldn't find my... Okay, cancel. So this is the one I want, right? Hang. Okay, never mind. Continue. Okay, so you already know how to use the Simulink to actually complete this block, the models. Okay, so from here, this one already explained. This one also explained already. Okay, you will get the result of this, and you will see the outcome actually having a delay, means the almost the 5 seconds or 5 units of time, there will be no response for your output due to the time delay. Okay, next. Now you are going to have this one. This one you've done already is the same example, similar. So now this one is the one we call as the closed loop. So I will put here some correction. So this correction here, it will be still open loop. Example 4 is open loop, is because of, you can see the diagram here. It is a straight line from the beginning and go to the end point. Same goes to the second input from the beginning, go to the end point. So this one is open loop. Open loop. Okay. Then the next example we have, so this one also the result from the same example, it is open loop. We call this open loop response. So this one. So after that, this example is closed loop. Some correction. I don't know why the slide changed a bit. The closed loop response, where you have your output here. So in the same example, let's say they do not give you equation. Let me check whether they give you equation. Okay, so they give equation. Okay, never mind. So now you having your output over here. Let's say your output is the same output they put here is Y. Okay, this is your output Y. So I will put this part equals to my Y. There is a turning point here. We call this, later you will learn this as a splitter. So this whole line is Y. So you'll be having the feedback, something like you are having your output already, then this output will actually finally make a change to your input U2. So this one is your GP. The D1 will be your GD. Okay, so this is the one we call as a closed loop response. You can practice later to draw again with 2 of the step inputs. And then this is a transfer function block from continuous library. And this one from continuous library as well. Okay, then you double click. You remember you will be having this bracket. So you will be using the num numerator and then denominator. So they will follow the polynomial equation. Like for example, A, B, C, D will be AS3 plus BS2 plus CS plus a number of D. So they will follow this pattern. So if you, let's say you only have 3 and 2, then it will give you 3S plus 2. If you only have 2, then it is just 2 lor. So if you have 4, 4, 1, then you'll be having 4S power to 2 plus 4S, then plus 1. I think you learned this one in the previous MATLAB lessons already. So this is the closed loop. So what is closed loop? Closed loop means you're having this one going back. Okay, so this one you can do it later. So now it's the same one, but with some addition. You have the controller over here. So I need you all to prepare this now using your Simulink window. Include all these, we'll be having 2 step input and then 1 PID controller. You just have to search for PID, and 2 transfer function block, and 2 transport delay, and also add block. So this one is add block. This one is transport delay. And here is transfer FCN, transfer function. And this is the step. And here is the PID controller. This one also step. And you're able to actually annotate like D3, U3, and so on. And you double click the transfer function block, you're able to put 2 and then 50, 15, 1. So do it now. And this one is the scope. Okay, so you will need this. So copy back. So go to your Simulink library. Okay. So sketch this. So many things here, so I need to close this one. No. So you all proceed first. Let me close everything. Everything. Okay. So, okay, you all proceed first. Where's my laptop? I closed everything already. Okay, very well. So you all proceed. Busy. So you prepare, you drag and drop all these relevant blocks first. Okay, so I'm going to have a new one. So new blank models. So you will need all this with the PID. So I think this will be the last for today already, which we name this as a closed loop response. Okay, copy and paste. Okay, so please do this one yourself. You will need 2 step input and annotate this one as D3 and then this one U3. So draw exactly the same. So this means this is the denominator 50, 15, 1 and the numerator is 2. Same goes to this one, the same one, 2, 15, 50, okay, 15 and then 1, the same one. So you just copy and paste for these 2 blocks. Your GD and GP, they are the same transfer function. And for the first one, the transport delay is 5. Same goes to the second one, the transport delay is 5. So again, you want to see all the blocks name, right? You just highlight and then you go to format and show the block name on. Okay, so this one is the scope. And the simulation time for this example is, what's the simulation time? They do not include the simulation time here. Did they mention? So let me check. So it's 50. So if I check the graph is 50, it means the simulation time is 50. Okay, so now we want to have this model. So the transport delay will follow everything the same like the previous question. You'll be having the transport delay of 5, unit of 5. So this is 5, this is 5 as well. Okay, now we include the controller in your block diagram. So where you find your controller, you just have to search for PID. Then you drag and drop, you can get this PID block. Okay, you double click the PID, you will actually have this. So this one is the type of the controller. The controller have few types here. You just click the drop down list, then you can select, for example, this example, they use the parallel. Okay, so this is the PID, and parallel, the equation for the PID stand for proportional, integral, and derivative. So we have the ideal PID, we have the parallel, we have the series, and so on. Okay, then how you key in the value of the P value, like you key in your controller during your lab section, right? So you can key in the value for the P, the value for the I, and the value of the D there. So let's say it is 1.65, 0.23, and also 2.97. So you will be having this one. Double click. Okay, so PID, PI, PD, P, and I. So from here, we have the PID, parallel, or ideal. Only two in this selection, drop-down list. So you choose the parallel. Okay, and then the value for the proportional is 1.65. The I value is 0.23. And the derivative value is 2.97. So the rest remain constant, don't touch. Okay. For your assignment later, you will see the keyword. If you have read the assignment, you actually can tune your PID, follow the transfer function, or follow, if let's say your input is sine wave, then you have to choose frequency response. For this example, we are using the input, both of them actually step input, step. So therefore, we are using the transfer function base. But we do not tune for this example. Tune means they will propose you the suitable PID values. Okay, so from here, you will just key in 1.65 for the P value, I is 0.23, and then the D is 2.97, and the type of the PID is parallel, and the controller type is PID. So you can choose the type of the controller. Okay, then okay. So you will get this. Simulation time is 50, so you change the stop time here, 50. You click the run. Okay. So when you click the run, I think it will be the same answer. Okay, yeah, same answer here. So the step by default is the step input of 1. So I do not change. So if let's say it is a step input of 5, the final value you just change to 5. So for this example, I put the step input of 1, which means this is the unit step input. Okay, so if you can check the observe from the graph we have, so this is very terrible performance, not good, very bad. It is because first thing is this one, there is a time delay. The output actually does not change for a period of 5 units of time, and it is having a very oscillatory response, and there is no steady state from here. So what you can do for this to improve is to increase the steady state time, meaning that let's say I change this to 1000. Okay, 1000. I just want to check when this process will achieve a steady state. So double click this. You can observe from here even worse. It is like super oscillatory. So based on this, you should do the tuning of the PID, fine tune. So let's say I use a transfer function base because my input is step. If my input, they are sine wave, then my option here, you should choose frequency response base. Because my input is step, then you have to choose this transfer function base. So you can tune error evaluating this one and that one. So you can read the error there because of we do not have the full version of PID tuning tool. We do have, just I didn't install just now. I just choose the Simulink and the MATLAB. So if you want to try this one for your assignment, you have to include the PID tuning tool. Okay, but license checkout failed. So imagine we have this one, then we can actually tune, meaning that they will actually suggest us the PID values for us, so that you will get a steady state. Like this one is super terrible, oscillatory. Even after 1000 unit of time, you won't be getting a steady state value. So what you need to do is you will actually having PID value adjust. You will adjust this. For example, I adjust this to a bigger number, 100. So let's see whether it become better or not. So run. Okay, then you will see this is the graph we have. So why it becomes so weird one? So let me check the time there. Okay, so this one also the same thing. So let's say I just run for 50. So you can change the value and test run. Okay, like for this example, the values go down and so on. So from 0, it go to negative value, even worse. Your set point is 1. So what is your set point? You can refer to this value. Your set point is 1. Same goes to your disturbance also. Set point is 1. So when you click this, you will see the PID value will change your response. So let's say I increase my I value to 100 as well. So you can run this and see whether it will improve your outcome or not. Like this one also not improving. So it is a try and error method. If let's say there are few methods that to actually get the PID values. We'll cover that I think week 10 or week 11, something like that. So for sure, for all the assignments, right, there will be some topics I haven't covered. So you have to self-read the topics. So all the lecture slides already posted to My Times. For the tuning one, you may refer to the lecture 10 and 11, maybe 9 also you can refer. Okay, so self-reading is important for all the assignments, for all the modules. They won't be like having all the topics covered only for your assignments to submit. So most of the time you'll be having some of the topics you have to self-learn. That's why you can see your assignment marks. They are very heavy, 20% per one assignment. So you have to put in some effort for your assignment. Okay, so continue. So from there, I think this one is just the PID controller. Just to introduce, you have the PID block and you can choose PI, P, PD from this drop-down list, and also the type of the controller. The one we have in our lab is actually ideal PID. So if you click the ideal PID, you can see the equation will change. So let's say this is the one I have. This one. So if I change this to ideal, so this will be the ideal equations we have for the PID controller. So what will be equal here? So equal, this is the transfer function for controller. You'll be having GC here, stand for the transfer function of controller. So GC. Okay, I think I cover everything for lecture 5 already. So yeah, that's all. Okay, so I stop sharing, stop recording. Okay, and don't leave. First, I need to mark your attendance. Okay, so please mark your attendance and check whether your name appear or not. So you can see the week 5, we cover the first order transfer function. We already learned the second order or high order transfer function, right? They all can be actually represented using the block of transfer function. We will be learning more examples next week. So Wednesday, 12 p.m., we'll be having this lecture 6. So same planning. If we cannot finish 12 to 2 session, then we'll be utilizing the evening session 6 to complete. Then you'll be having your test on Wednesday, week 7, covering all the topics from week 1 to week 6. Okay. Oh, sorry, I already stopped sharing, huh? My mistake. Okay, so thank you. Okay. Okay. Okay, done for this week. So please start your revision for your test. Goodbye and see you all next Monday, our lab. So Monday lab, we will start our lab at 9 o'clock. You may come early to prepare, especially for the level control. You can ask your friend who has done the level control, and we need to prepare the equations to calculate the PID values. Early preparation is very important so that you can go back early. Like that day, we actually took about 4 hours, right, to finish. We left at almost 1 p.m. So if you prepare early, you can actually finish everything within 2 to 3 hours actually. You can go to ask your friend who has done the first lab. So for example, I think you can ask, I can't remember who did the first lab already, the level control. I totally forgot. But you refer to the timetable. You ask your friend what you need to prepare. You need to bring your laptop. I think you bring 2 laptops so that 2 of you can work together in one group. Okay, that's all for today. Thank you. Bye-bye.
Sorry, Miss. Miss.
Miss left you, Junhan.